In this video, our next goal is to consider the different methods that are used for computing probability. The first one we'll consider is the classical probability assessment method, which advocates that it is a method of determining probability based on the ratio of the number of ways an event can occur. We denote that as M, compared to the number of ways any outcome or event can occur when the individual outcomes are equally likely. I have included a picture here, the picture of a die, or a pair of dice, if you will. Let's consider for simplicity purposes, if, emphasis on the word if, you threw a die, what is the probability of getting a 2? What chances do I have that the outcome observed is a 2 that turns up? Well, I would say 1 out of 6. Well, the 6 here represents the number of possible outcomes since it's a six-sided die by standard, and 1 is the number of ways that 2 occurs as a possible face on this die. So, in what if scenarios, if I were to toss a die, what method would you use to compute or assess the amount of probability that can be ascribed to an event of interest? The particular method that we'll be using in that case is the classical probability method. Next, you have the relative frequency assessment method, which advocates that we should compute probability as the number of times an event occurs or has occurred divided by the total number of times that experiment was performed, possibly in a large number of trials. So we use this method especially in cases where we can access real data of how frequently an event of interest has occurred in the past, and we use that knowledge of the past to predict the future. Take, for instance, if you were to buy an item on Amazon and it has been indicated that 9 out of 10 times in the past, based on real data, verified the reviews and purchase records, 9 out of 10 times in the past, or customers have returned this product. And I ask you, what is the probability that this same product you're buying will be returned on the 11th trial? Well, based on past data, you say 9 out of 10. That is using the relative frequency of how often this product has been returned in the past to assess the likelihood that it will be returned on the 11th purchase. Then third, we have the subjective probability assessment method, which is a method that defines probability as reflecting a decision maker's state of mind. The decision maker is usually an expert. So it could be an expert's state of mind regarding the chances that the particular event will occur. This is often used in cases or situations where an expert opinion matters. This is usually what you find if you have, in a court case, if you have invited an expert to comment on a particular incident and they give a subjective assessment of how likely an event will occur, that will be the case of using subjective probability assessment. Here are a couple of examples. I'm going to take that out and want to indicate what method of probability assessment will be most likely used to assess the following probability. A, what is the probability that the customer will return a purchase for a refund? Since we can access real data on how often that refund has happened for that particular product, we should use the relative frequency assessment method, in which case we're using the data available to assess how often it has happened in the past in order to predict the future. B, an inventory of appliances contains 4 white washers and 1 black washer. If a customer selects one at random, what is the probability that the black washer will be selected? Well, this is a what if scenario. And a what if scenario to calculate probabilities will be best served by using the classical probability assessment method. So you have classical probability assessment method. All right. With that in mind, whenever we compute probabilities for events or things that happen in everyday life. So this is a perfect segue to look into the different types of events for which we're going to compute probabilities in this course. The first one is mutually exclusive events. You see, two events are said to be mutually exclusive if the occurrence of one event prevents the occurrence of the other event. I have a picture here where you have the head of a coin and the tail of a coin. You would likely agree with me that if you were to toss this coin once, you are either going to get either a head or a tail. So the event of getting a head and the event of getting a tail cannot both occur. It's an either or scenario. Either you get a head or a tail. If you get a head, it prevents you from getting a tail in the single toss of a coin, and vice versa. That is, if you get a tail, it prevents you from getting a head at the same time. So the event of getting a head and the event of getting a tail are said to be mutually exclusive of each other because the occurrence of one prevents the occurrence of the other. Another quick example is if you pull up to a T junction, the event of turning left is mutually exclusive of the event of turning right because both events cannot occur. It's either one of them occurs and thereby prevents the other from occurring. Then we talk about independent events. In statistics, two events are said to be independent if the occurrence of one in no way impacts or dictates the occurrence or non-occurrence of the other event. Take, for instance, if you were to throw a pair of dice, the outcome on the first die is definitely independent or not dictated by the outcome on the second die. So, outcome on one die is independent of the outcome on the other die. On the flip side, we have dependent events. You see, two events, as the name suggests, are dependent if the occurrence of one affects the probability of the other event occurring. So, for instance, if I were your professor in a physical face to face class and I told you that I would not be coming to class, well, I'm sure more likely than not, it won't make any sense for you to be in class. So, the event of you attending class depends on the event that you assume that I'll be coming to class. These are dependent events. All right. Next, we're going to start talking about the mathematics of computing probabilities of events. So, we talked about mutually exclusive events, so it makes sense that we should learn how to compute the probability of mutually exclusive events. Mutually exclusive events are otherwise known as disjoint events. Here is a visual for you. These are events where if one occurs, it prevents the other one from occurring. So they have nothing in common. Nothing in common. Okay? So, for instance, if we roll a die, the outcomes that you can get a 1 on the die and that of a 2, in a single roll of that die, they are said to be disjoint or mutually exclusive because they cannot both occur. Here's an example of data in the table below, which represents the results of a survey in which 200 people were asked their means of travel to work. Suppose each person only uses one and only one of the indicated means of what transport. Bearing in mind that fact, we are to answer the following questions. Well, for the means of transport, you have drive alone, carpool, public transport, walk, other means, or walk at home. And we're to use the survey data to build a probability model for the means of travel to work. Well, using the relative frequency method, the probability that I'll pick one person out of these 200 people who drives alone will be 153 out of 200. Okay, and that is the same as 0.765. If I want to write it in decimals, that's not necessary. The probability that I'll pick a person who carpools is 22 chances out of 200. For those who make it to work using public transportation, it will be 10 out of 200. And then similarly, 5 out of 200 for those who walk to work. And those who use other means, 2 out of 200. And those who work at home, that will be 7 out of 200. Notice that each of these probabilities is a number between 0 over 200 and 200 over 200. And the sum of all of these probabilities is 1. So this is definitely a fitting description of a probability model. Based on this probability model, we consider part B of the question. This says to estimate the probability that a randomly selected individual carpools to work and interpret your results. Well, for carpooling, here it is highlighted here. Using the relative frequency approach, the probability that the person carpools will be equal to 22 over 200, or if you will, 11 over 100, or 0.11. That's also allowed. Question C. Would it be unusual to randomly select an individual who walks to work? How would we qualify an event as either unusual or usual? The way to go is to consider the probability. Well, why are we considering the probability? Probability will measure how likely or how frequently it occurs. So if it happens rarely, then it becomes unusual, surprising, extreme. If it occurs often, then we say it's not unusual, it's just typical. So let us consider the probability of those who walk to work. Of those who walk, that is, in this case, those who walk. This is 5 over 200. So 5 over 200, that is the same as 0.025. Is this too small? This represents about 2.5% of the time. Well, usually, as a standard, we usually say the probabilities lesser than 5% for classroom purposes only are considered what? Unusual. But please, this is not always set in stone. As I said earlier, this is only used for classroom examples. In the real world, if you're making what planes, or if you're considering flight accidents, what makes it rare could be significantly lesser than 5%. I am pretty sure that if 5% of the time there are flight accidents, a lot less people will be taking flights. So, flight accidents occurring and being considered unusual will be a case where you have what? Something even lesser than 5%. So again, to emphasize, the 5% here is taken as a theoretical threshold, not a fixed threshold in practical use. All right? When we want to compute probabilities for disjoint or mutually exclusive events, how do we go about it? Take, for instance, remember that in this context, we were told that if one person uses one and only one means of transportation, that means that a person, once they decide to what? To carpool, they can no longer drive alone. The events drive alone and carpool, or relative to any other of these possible outcomes, is considered a mutually exclusive event, or are considered mutually exclusive events. So, how do we compute probabilities for mutually exclusive events? We use what is called the addition rule. Let me give you an example. For instance, if I'm asked to compute the probability that a person carpools or walks to work, Well, that would mean I have to consider the probability that the person carpools separately and the probability that the person walks to work separately and then add them together. That is what the addition rule for mutually exclusive events, since one does not what have anything to do with the other. So you compute their separate probabilities and you pull them together in an additive fashion. So in this case, you have what? 22 over 200 plus probability of walk. That would be what? 5 over 200, which gives 27 out of 200 as the probability for these two disjoint or mutually exclusive events. In general, when A1 represents an event relative to A2, which represents another event, and both of them are disjoint outcomes, we use the addition rule for disjoint events, which involves computing their separate probabilities and then adding them together. All right, let us look at what happens if the events are not disjoint. So, what formula should we use, or what adaptation to that formula would be involved? Here is an example to gradually get us there. In this example, the sample space for an experiment is S equals 0, 1, 2, 3, up to 9. So I'm going to write that here. I'm going to define an event A, a subset of this event. It is a subset because all the points here are right here for event A. And then we have another event B, whose what? Whose outcomes are right here. So our interest is to find the event A or B and use it to determine the probability that you get event A or B. As a visual aid, I'm going to draw event A as 1, 2, 3, 4, 5, and then event B as an overlapping what? Circle where you have 4, 5, 6, 7, and 8. And based on this, I will also note that in my sample space, 0 has not been accounted for, neither has the number 9 been accounted for. So I'll put them in the box for the sample space. Then I can proceed to find the points in event A or B. In event A or B, you have 1, 2, 3, up to what values? What numbers are in A or B? As I'm shading, you might notice that that will be 1, 2, 8. So, based on this, can I find the probability of event A or B? That will be how many points do I have in A or B out of how many points do I have in the general sample space? How many points in A or B? 1 to 8, that is 8 out of what? 10 chances in the whole sample space. Okay, so keep in mind, I'm going to need this result later. The probability of A or B is 8 over 10. Okay, the use of the word or in this context is used in the inclusive sense in statistics. This means it includes both those who are in A only, those who are in B only, in other words, A or B, and those who are in A and B. Let us consider the AND event. You see, you will notice that in this event, in the case of these two events, these events are not disjoint because they have something in common. So, what do they have in common? What if we're told to find the probability of what is common to both A and B? Using the same diagram we had earlier, so I'm going to bring that diagram here. So you have what? A, and then again B. You have 1, 2, 3, 4, 5, 6, 7, 8, 0, and 9. In order to find the event A and B, the event A and B is made up of the points 4 and 5. And based on that fact, if we are to find the probability of A and B, that will be the number of points in both A and B divided by the number of points in the sample space. That will be equal to, how many points do we have in A and B? 1, 2. So that will be 2 out of what? 10. So take note that for not disjoint events, because they are not disjoint because they have something in common, the probability of A and B in this example is 2 over 10. I want us to keep track of the results we're getting because we're going to pull them all together soon. All right? Let's look at another case here. What if we're told to find the probabilities of A separately and then the probability of B separately? Probability of A separately will be how many points are in A. I'll call it number of points in A all over the total number of points in S. That'll be 5, 1, 2, 3, 4, 5, 5 out of 10. A similar argument can be made for probability of B, where the number of points in B all over the number of points in the sample space will be how many numbers do we have in B? That is another 5 over 10. Now you see all the results we have had so far. Let's pull them in this observation. Can we find the value of probability of A, which is 5 over 10, probability of B, which is 5 over 10 added together, minus the earlier result for probability of A and B, that was 2 over 10. Well, 5 of 10 plus 5 of 10 minus 2 of 10, that will be 5 plus 5, 10, minus 2, that is 8 over 10. Have we seen this result before? Let us go back. We got that result in what? Probability of A or B. So I am going to say that it appears that whenever we have not mutually disjoint events, this result will give us probability of A or B. And we have a formula on our hands. That formula says that for events A and B that overlap, which means they are not disjoint events, they have something in common. So let me put it that way. For this kind of events, we have the general addition rule of probability. And the general addition rule of probability says that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So that is very crucial. So this holds for not disjoint events. But you might notice that this says for two events, disjoint or not. Well, why does it apply to disjoint events? Because if you go back to disjoint events, you will notice that the probability of carpooling and driving alone, if you are only allowed to what? To use only one means of transportation, is the probability of an impossible event. In the beginning, we learned something very crucial, that the probability of an impossible event is always 0. So if we talk about, about the scrolling up, I wanted to reference that. So the probability of two mutually exclusive events being associated with and is definitely what? 0. So in this case, if you have disjoint events, this probability is 0. In which case it just reduces back to the old formula for disjoint events. So take note of this part, that this is why it is called the general addition rule, because it applies to both disjoint or not disjoint events. In which case, for disjoint events, this guy just goes to nothing, and you only have this remaining part. All right. We will now consider some problems in the next video to illustrate these formulas.